I'm using my this. Where this is the Ricci tensor, this is the scalar curvature. This is called the cosmological constant. And this is the energy momentum tensor. This equation really describes what GR is all about. So it's the relation between the geometry of the universe with the matter contained in it. So we can see that in this side, all these are geometric quantities. Here, all the geometry happens, and here is the matter. Of course, as we're saying that these equations model the universe, we expect that they are not going to be easy to solve. So, really, if you write this down in a special set of coordinates, you can see that actually this is composed by a system of hyperbolic PDEs. So, if you don't do PDEs, then this is an issue. Of course, if you like hyperbolic PDEs, then this is great. But one point of view that we can take to study the solution of the Einstein equations is initial value problem. So we focus on initial value. Which might be more appealing for those who like more elliptic PDEs or Riemannian manifolds. And the idea is pretty simple and it's pretty nice. So suppose that this is our space-time, and what we are going to do is consider a hypersurface. Actually, it's going to be a space-like hypersurface. We call it G. And what does a space-like mean? This means that the unit normal nu is time unit. And of course, this means that the norm with respect to the Lorentzian metric is -1. So, if we restrict the Lorentzian metric to this hypersurface, what we are doing is killing the signature of the Lorentzian metric. So actually this restriction is a Riemannian metric. So now this is going to be is going to play the role of the initial value in our initial value problem, in our Cauchy problem. We have existence theorem that says that when you prescribe one of these guys in a precise way, then you get local existence of space-time. So instead of studying Riemannian manifolds, we can switch to this point of view and studying geometry of, instead of studying Lorentzian manifolds, we can switch the point of view and just study Riemannian manifolds. Of course, we cannot just arbitrarily give a Riemannian manifold and hope that that's going to be part of the space-time. We need to satisfy some equations, of course, because we are supposing that our ambient satisfies the Einstein equation, so of course this is going to impose some constraints here. So I'm not going to spend a lot of time on this, but the Einstein equations give constraints. And I'm going to leave it like this. And the long story short is that, I'm just going to write it as a definition, an initial data set for the Einstein equations. And this is something technical, but I need to be a little bit more precise here. I'm going to be assuming that it's time symmetric. What time symmetric means, you can imagine that this a space like a slice is geodesically complete inside the Lorentzian manifold. And I'm also going to assume the dominant energy condition. And this is a condition that tells us that our initial data set is physically relevant. I don't want to go too far on this because I want to get to the point. So this is going to be a Riemannian manifold Mg, such that the scalar curvature is bigger or equal than the cosmological constant. So that's why this condition is going to appear in all I'm going to do now. So that's the motivation why all my results are going to be dealing with manifolds with lower bounds with scalar curvature. Okay, so I think to motivate all this, the best way is to start when the cosmological constant is exactly equal to 0. So in this case, one can think that, of course, the initial data sets that we want to consider now are those with scalar curvature non-negative. And we are going to restrict ourselves a little bit more. So in this setting, we are usually interested in isolated systems. So that means you can imagine a collection of stars, collection of galaxies, collection of black holes, but everything in a finite region of your space-time. So if you think about it, if you move away from this cluster of black holes, let's say, the gravitational energy, or the gravitational field is going to be weaker. So you can imagine that if you go sufficiently far, you're going to be like in an empty space. So you're going to be close to Minkowski. At the level of initial data sets, so we say that a manifold Mg is asymptotically flat. And I'm going to denote this by AF. If this metric G approaches the Euclidean metric at infinity. The way that we can think of this, you can imagine that maybe you have some weird topology in your manifold and it's not behaving nicely, but if you move away from this region, then your manifold is going to look very nice and the metric is going to become Euclidean. The good thing about this is that if we add here appropriate decay conditions, so we are going to add that the derivatives of the metric goes to 0 sufficiently fast, then we have a well-defined notion of total mass. Called the ADMS. So this is something really, really nice about this asymptotically flat initial data set. So I think it's a good moment to show an example. Of course, Rn is an example of this. This is a Riemannian manifold with scalar curvature equal to 0, and it coincides with the Euclidean metric, so trivially is one of these. But probably the most important example, which is non-trivial, is the Schwarzschild, the spatial Schwarzschild manifold. And of course, it's called like this because it arises as a t equals 0 slice of the Schwarzschild space. So that's your corresponding initial data set. The metric, the manifold, is given by this. let me just do it in n equals 3. Here, let's just say, for simplicity, m bigger than 0. And the metric is given by where this is the standard metric. So we can directly see that this is asymptotically flat. So meaning that we go to infinity means that r goes to infinity, so this goes to 1, and we obtain the metric of the Euclidean space in polar coordinates. So it's asymptotically flat. If you want to check more properties, the scalar curvature of this is equal to 0. And of course, it happens what we expect. The ADM mass of this is precisely this parameter m. Now, I want to mention something. If you notice, when r equals to 2m, this metric becomes singular, but this is only a problem of the coordinates that I'm using to describe this metric. So really, this surface r equals to 2m, which is, in the way I'm putting it, is the boundary of this manifold. We have what is called horizon. And horizon here, every time I say horizon, I'm going to mean that the mean curvature is equal to 0, and it's our minimizing. Meaning that any surface that encloses the boundary has to have bigger area. The picture that we can have in mind, just the rest of the top. It's nice to have a picture like this. So, really, something like this. It's rotational symmetric. This is r equals to 2m. This is our horizon. Good. So now I want to try to convince you that this manifold behaves really nicely, and we actually know a few things about them. So let me state the first cornerstone theorem in this setting. And that's the positive mass theorem. So this theorem was proved by Shane and Ya in, I think, 79, and again in 17. So in 79 they proved for n equals 3, and then they extended it onto dimension 7, and then finally in 2017 they proved it for all dimensions, and by reason, I think this was in the 80s, I don't remember. And this was for all dimensions, assuming that the manifold was sphere. So pretty much what it says is that if you have one of these guys, Riemannian manifold with non-negative scalar curvature, then it happens what you expect. That is, the ADM mass of this is not negative. Moreover, we have a rigidity statement which says that the ADM mass G is equal to 0 if and only if this guy was isometric the Euclidean space. So this is really nice, this rigidity result is really important. And this actually leads to the main question in this talk. So we see that we have the rigidity statement, so then it's very natural to ask if the ADM mass of a manifold is close to 0, is Mg close to Rn. And of course, once I write this, if we have a lot of people working with convergence and things like this, we need to be precise what we mean by close to. So let me just put this here on this. The answer is no in general. So no. I think it's good to have at least one example in mind. So let's consider the Schwarzschild manifold and construct a sequence of Schwarzschild manifolds in such a way that we make the horizon smaller. So the radius of the horizon is smaller. So something like this. And then we can try something like this. So you can see how the mass is going to 0, but this sequence of manifolds in any nice type of convergence that you can think of is not going to go to R. So this is just to motivate that this question makes sense, and we need to be careful about what we mean by close to and find a way to make sense of all this. So it turns out that, let's see, this is charged down. So one good idea is to restrict to graphs. And we need to be precise what we mean by that. So suppose now that I'm going to have one of these guys, an initial data set in non-negative scalar curvature, and I'm going to assume that they can be isometrically embedded into Rn plus 1 as a graph over Rn. So what I'm thinking is you have your manifold Mg, and now we are going to assume that we can see this as a graph of a function f over Rn plus 1. Well, the graph is going to be in Rn plus 1 with the induced metric by Rn plus 1. So, good. So, which type of functions are these? I mean, we need to be careful and define our family of functions carefully. So, let me state this as a definition. This definition is due to UNAM 2011. One rule. In 2014. So suppose we have a function from Rn minus a bounded with connected complement. And we are going to ask that f is continuous, so probably I can write it like this. And smooth outside this end. And I'm going to assume also that the limit when x, the modulus of x goes to infinity is constant. Or goes to plus minus infinity. I'm going to assume also that the derivative or the gradient goes to 0 at infinity plus decay conditions. I don't want to become too technical here, so just assume that it goes to 0 sufficiently quick. And I'm going to make a few definitions here. So let me continue here. If this set is empty, we say that f is entire. And we say f has a minimal boundary. If f is locally constant, on the boundary, and the derivative goes to infinity at the boundary. Probably I should say something here. So this is the definition, of course, of an asymptotically flat graph or function. I'm going to be switching back and forth with this. Okay, so I think these assumptions are reasonable given the assumptions on asymptotically flat manifolds. What could be a little bit intriguing is this condition. But this simply means that when we have a minimal boundary, this condition is guaranteeing that the gradient is going to blow up at infinity. And if you write that in terms of the graph, this means that the boundary is minimal. So we have a horizon. So that's why that condition is important. A bit, because I just told you we have a well-defined notion of ADM mass, and I didn't comment on that. The thing is that the formula for the ADM mass is a little bit complicated, and I didn't want to write it then because now I'm going to write it for the case of graphs. So of course, in particular, a graph is going to be one of these manifolds. So we have an ADM mass, and we can write it in the following form. So if f is an asymptotically flat function, or graph, however you want to call it, the ADM mass of the graph is going to be equal to 1 over Cn limit when r goes to infinity, where SR 1 over df Fii Fj minus Fij Fj mu j dsr, where here Cn is this constant, Sr is the sphere of radius r, guess unit normal outward to the sphere. So that's our formula for the ADM mass in this setting. And just so we have an example of these things. Of course, if we expect this to be meaningful, we better make sure that we have Schwarzschild manifolds here. So the Schwarzschild manifold mass M is given by f of r. Remember that is rotationally symmetric. By this graph. So precisely when r is equal to 2m, we have a horizon. You can check that the derivative blows up. And if you graph it, then you're going to get something similar to this, but inside Rn plus 1. Okay. Good. So now, to convince you also that it's a good idea to work with graphs, let me show you an alternative expression for the ADM mass. So this was a key observation by Lam. And it's the following. It turns out that for an asymptotically flat graph, we can if this guy is a level set, we can assume smooth. So just think as h as a regular value of f. And let me just say that this, of course, has to be this. Then the ADM mass of f is going to be given by 1 over Cn, the integral of Rn over h of the scalar curvature with respect to the Euclidean, plus 1 over Cn, the integral of the mean curvature of this level set and this. So we have a really nice expression for the ADM mass. Why is so nice? Just think for a second, like if we know that the mean curvature on this sigma h is not negative for some reason, and of course we always assume that the scalar curvature is not negative, so then we immediately get the positive mass theorem. So hopefully this motivates the fact that using graphs is a good idea to investigate this type of problems. So it turns out that in this setting, the answer to this question is true in some sense. So this is a theorem by Wang and Li in 2015. And this says that let n be bigger or equal than 5. So if mi is a sequence of asymptotically flat graphs with non-negative scalar curvature, and such that for almost every level set such that almost every level set is strictly mean convex. This means that the mean curvature of this level set, of course the level set lives in Rn, right? So the mean curvature of this level set is strictly positive, and they are strictly constant and outer minimizing. Then, if the ADM mass of these guys go to 0, then MI converges to a plane. So let me write this in the following way. So this sequence converges to this in the sense of currents. So at least for asymptotically flat graphs, we have a nice result of convergence, or we can say stability of the positive mass theorem. Of course, I need to make some remarks here. I'm not going to spend a lot of time on this one. I just want you to notice the conditions and to keep in mind what are the conditions, because I'm going to have similar conditions and I'm going to explain them when I use them. So here we are assuming strictly mean convex. Of course, we need to assume this to be in the set of manifolds that we're interested in, outer minimizing. This, I'm going to be clear on what that means. So for now, just believe that there is a plane that you can find on which this convergence is going to make sense. And of course, every plane is isometric to the Euclidean space, because it's just a level set. And then I won't have time to explain this carefully, so I'm going to do that with pictures at the end. Okay, so this was for n bigger or equal than 5. So what I'm going to, let me add this. If n is equal to 3 or 4, one more condition is needed. In my case, I'm not going to require this condition. Everything is going to work for all dimensions. Just if you're curious what is this extra condition needed, is they kind of restrict to manifolds which are not too far away from Schwarzschild manifolds. In some sense, they are close. This is a technicality that I'm not going to use. Good. So this works for asymptotically flat. So now the natural question to ask is, okay, so what happens if the cosmological constant is negative? And in this case, well, this leads to asymptotically hyperbolic manifolds. And of course, what this means is that now my Riemannian manifold is going to, or for my Riemannian manifold, the metric is going to converge to the hyperbolic metric. And infinity. So now, remember the dominant energy condition was scalar curvature bigger or equal than lambda, and we can normalize this to make this equal to this, which is precisely the scalar curvature of the hyperbolic space of dimension n. So we want to repeat this story. So I think I want to get to the point, just believe a few things. So in this setting, we also have a notion of total mass, which I'm going to be calling the hyperbolic mass, or simply mass, and I'm going to denote it simply by m, so no subscript anymore. And I think, well, the definition of this mass is more subtle than the one for asymptotically flat. So yeah, I don't want to discuss any of this. Just let me mention that the positive mass theorem in full generality is not proven yet, I think. It's proven in some cases. And for us, it's really interesting to see which results that we have for asymptotically flat manifolds carry over to asymptotically hyperbolic manifolds. Okay, so I think that's all I need to talk about this. Okay, so what's the theorem that we want to show, or that we should show? Yeah, if there are any question, please ask. Theorem. And mi be a sequence here. Might be a sequence of asymptotically hyperbolic manifolds graphs in Hn+1 with scalar curvature bigger or equal than this for n equals 3, and mean curvature vector pointing upward. Suppose that almost every level set is star-shaped and outer minimizing. In the hyperbolic plane, of course. Let mi denote the height be the mass of this. And let me write in a more precise way what they have in here. So normalize the height of the level set so that it has volume equal to this number, and actually this is going to be defined as H naught. No, not really. No, let's just not do this. B here is just a constant, a fixed constant, arbitrary. Then if the masses goes to 0, then these guys approach to the hyperbolic space or to the plane S equal in the sense of coordinates. So a few remarks here. So this is similar to that condition. I have this extra one, and the reason why it doesn't appear here is because in this setting, the fact that you have a non-negative scalar graph implies that condition. So we don't have it in this setting, so we need to put it. We have it in some particular conditions. Instead of having strictly mean convex, I'm going to have a star shape. I still need this condition of outer minimizing. And this H0 is precisely where this quantity is realized as a volume of a level set. So this normalization means that you have your graph, find the level set where this volume is realized, then translate all your elements in your sequence so that this level set coincides with the plane S equals 0 to the, in this case will be the Rn, the x n plus 1 equals 0. And then once you do that normalization, then your manifolds are going to converge precisely to this plane. Okay, so before discussing the proof, let me fix some notation and the setup of this. Just let me see how much time I have. Okay, so now we need the corresponding definition for asymptotically hyperbolic graphs. This is mainly due to Dahl, Jiquot, and Sakovic. And the definition is going to be very similar. So now you have a function define Hn going to R. And this is going to be asymptotically hyperbolic. Of course, if the same condition, so omega is bounded, the complement is connected, and all this. I'm going to have the decay conditions. So let me denote E equal V squared df f has the right decay. 2, I'm going to require this guy going to 0 at infinity. And of course, similar definition for entire and minimal graph, a minimal boundary. Of course, here, this is this. And this doesn't make any sense if I haven't told you what is Hn for me. So let me just do it here. So here I'm thinking of Hn as, so let our theta be polar coordinates on Rn. So then B takes the form dr squared plus hyperbolic sine of R sigma. Again, sigma is the usual metric on the sphere, Sn minus 1. And of course, I need to tell you what is Hn plus 1, because that's where our graphs are going to live. So this is simply Hn cross R with the metric given by this plus B, where this B, as I mentioned here, is the cosine square ds plus dr squared plus sine or sigma. You can check that this is really a model for the n plus 1 dimensional hyperbolic space. And those are going to be my graphs. The good news, and this was hard work by, again, Dahl, Gicot, and Sakovic, just as in the asymptotically flat case, we have a very nice expression for the mass, for the hyperbolic mass, which I'm going to write down now. So, if f is asymptotically hyperbolic, the mass of f is going to be given by this seemingly complicated formula. So it looks more messy, but has a similar flavor than the ADM mass. So that's how one aspect this is going to work. Sorry, so this is due to Dahl, Gicot, and Sakovic. So now let's go to see how the proof works. So here, I don't have time to explain this type of convergence. Let me just make a remark. If, say, U rho is an H ball, I'm going to be precise on what I mean by this. It is enough to check that the flat distance, so this is the Federer-Fleming distance in this ball between the graph and this plane that we have normalized is bounded by a constant times a power of the mass of the function. So then you can see when m goes to 0, then this distance is going to 0. And it's standard to take this fact and just put it so that it implies this convergence in the sense of coordinates. Sadly, I don't have time to really show you how to do that. Okay, so let me just quickly give you a picture on how the proof works. So suppose that we have Hn here. This is S, and we have an asymptotically hyperbolic graph. Let me just draw with the horizon. Like this. And as I said, we need to pick some H naught, which the definition is already there, but let me put it here. So this is going to define a plane here. And our goal is to show that, or to compute what's the flat distance between the graph and this plane. Here I'm writing this inside this H ball. What I mean by H ball is simply the corresponding ball in the hyperbolic space. So it's not going to look too round. It's going to look something like this. Oops, ugly. Say something like this. And now I will ask you to believe me that the flat distance between these two are going to be given in principle by the volume between them. So we want to compute the volume here, so this is all around this, the part below H naught, and in addition, we also need this area. So how long do I have? Okay, so really quickly. Let's say this is region A, this is region B, and this is region C. So for region A, so we need to compute this area. So we can use the isoperimetric inequality to just bound this area in terms of the area of the boundary. Well, this volume in terms of the volume of the boundary. And the volume of the boundary is a nice fact that in GR, in the asymptotically flat and in the asymptotically hyperbolic, at least for graphs, we can control the area of the boundary by something called the Riemannian-Penrose inequality. So this region A is going to be controlled. So the volume of A, I guess I need to be precise here, inside this ball is controlled by a constant times M. For the region B, that's precisely where the definition of H naught is going to be. So H naught is precisely where we have this volume. So whatever we have in here is going to have less volume that this level set. So now we can integrate from here to here. So B is going to be bounded by a constant times rho times M. I think I can use just simply M. Yes. And the last part is C, and that's the more complicated. So some work following Wangley gives you an estimate on the supremum of F in terms of the mass to this factor, to this power. And then you can use this to approximate C. So volume of C is going to be less or equal than a constant times rho to the n m1 over n minus 2. So we have controlled these three. So if we add those three, we are going to, we have shown that the distance between this graph and this plane is less or equal than some constant times the mass to a power. And by normalizing, then we can get this result. And I think I'm going to stop here. Well, the problem with positive cosmological constant is that you don't have the asymptotics anymore. Like your level sets are going to be compact, so at least these techniques are not going to. I think physicists are trying to come up with a mass, and some mathematicians have some mass, but like no site is happy with the other site definition. Well, that's part of the subtleties of the asymptotically hyperbolic. For asymptotically hyperbolic, you can have different conformal infinities, and it depends which one you have is the definition of mass that you use. In this case, it's going to be a spherical conformal infinity, and that's the one that we. I mean, I have to say that I'm not familiar with like how all this story of the asymptotically hyperbolic manifolds came into play. I know that from the physics side, it's related to the ADS-CFT correspondence, and that's all I know about it. From the mathematical side, it's interesting because it shares some features with the asymptotically flat, but I mean, it's clear that some of them are missing, and some of them are improved somehow. So for example, in Riemannian, in asymptotically flat, we have the celebrated Riemannian Penrose inequality, which pretty much is bounding the mass of the horizon of a black hole. But for asymptotically hyperbolic, we don't have it yet. That's the mathematical side of it.